We are going to continue to talk about using trigonometry, which if you'll remember from last time, trigonometry is the study of triangle measurements. And we looked at these three specific trig ratios or trigonometric ratios, sine, cosine, and tangent. And we looked at what those are in class as well. But we're going to take that a step further, and rather than just finding the missing sides using this, we are going to find missing sides using a lot of different techniques and problem-solving strategies. Excuse that bell. Okay, but first what we're going to do is we are going to find our trig ratios when we're only given one ratio. Instead of being given side information, we're given one ratio, and we should be able to find the other two. Because these ratios work for any size of triangle, we don't have to worry about the actual specific measurements. We can use the numbers given. Okay, so we're going to get started right now. I do want you to remember before we write anything else down, we have an acronym that helps us remember what the sine, cosine, and tangent ratios stand for. And that is SO, CA, TOA. Okay, so CA helps us remember that the sine ratio is always opposite leg over hypotenuse. The cosine ratio is always adjacent leg over hypotenuse. And the tangent ratio is always opposite leg over adjacent leg. So in this first problem, we are given that the tangent ratio for this triangle of this symbol is called theta, by the way. This is new information for most of you. This is a Greek letter, theta. Okay, it's a Greek letter. You've used Greek letters before in math. Pi is a Greek letter. Okay, this is not pi though. Okay, this is not actually a number that we would know where pi is. Pi is about 3.14. But mathematicians, because we get a lot of our math from ancient Greece, they used these letters to represent unknown values. Well, theta always represents, okay, 0 with a little horizontal line through it. Theta is always a missing angle measure. Okay? So all we're doing is saying that one of these angles, we're calling it theta. Rather than call it x or y or z or any other letter, we're going to use theta. That's all that means. Don't want to confuse you with that. But if that is our reference angle, the tangent ratio is 5 over 12. Okay? Now, this is a very generic triangle, and in fact, both these sides look to be about the same length. But what the tangent ratio is the opposite leg over the adjacent leg. So these two numbers represent opposite and adjacent. So all I'm going to do is I'm going to identify one of the acute angle measures. For our purposes today, theta is always going to be one of the acute angles, meaning not the right angle. I know that measure, it's 90. I'm going to pick one of these letters to be theta, or one of these angles to be theta. So I'm just going to mark theta in that corner. That's an angle measure. It's like calling this angle A or B or whatever I want, but we're using that Greek letter as our placeholder. Then the opposite leg from theta would have to be a 5. The adjacent leg to theta would have to be 12. So I'm going to go opposite the triangle. So this is a 5. And then the adjacent leg to theta is 12. Well, in order to find cosine and sine, okay, this is still adjacent. This is still opposite. But I need the hypotenuse. In order to find the hypotenuse, we are missing that side of the triangle. Remember that we can always use Pythagorean Theorem. Okay? So we're going to call our opposite leg the A, our adjacent leg the B. We're looking for the hypotenuse C. Okay, that's 25 plus 144. When I add those, I get 169. And this works out to a nice, neat, exact number because, ignore that bell also, the square root of 169 is exactly 13. So that's my hypotenuse. Now I can identify sine of theta and cosine of theta. Because the sine of theta is the opposite leg over hypotenuse. Well, the opposite leg was already a 5 over the hypotenuse of 13. And the cosine ratio is the adjacent leg, 12, over that hypotenuse of 13. Sorry, getting a little tongue-tied. So that is how we find these other ratios if I'm given one of the ratios. So what I would like for you to do is take this opportunity, pause the video, and try and do this bottom example like we just did the top one. But this time you're given cosine of theta is 5 over 7. Remember that cosine is the adjacent leg over hypotenuse. So like I said, pause the video, give yourself time to do this. When you are ready, you can click play. And these are the answers we should get for this triangle. When we label one of these two angles as theta, normally I'll just kind of stick with the same one because these pictures are identical, but I'm going to use this as my theta. The cosine ratio, remember from SOHCAHTOA, is adjacent over hypotenuse. That means if this is angle theta, the adjacent leg, the leg that is right next to that theta symbol for this angle, is the 5. The hypotenuse has to be the 7. That means I'm looking for this opposite side, which I called A. You could have called it X, Y, Z, any letter you wanted. But since we're dealing with Pythagorean Theorem, I just called it one of the legs, A. I'm looking for that. So I set up my A squared plus B squared equals C squared with 5 in for one leg, B, and 7 in for the hypotenuse, C. And when I work through my Pythagorean Theorem, I get that A is approximately 4.9. Okay? Now, obviously, these drawings are not drawn to scale. Okay? 5 and 4.9 are really, really close to the same length. So this is pretty close. With the other one, it was a little bit different. But all that does is allow me to set up my sine ratio and tangent ratio. Sine is opposite leg, which that 4.9 was opposite the theta, over hypotenuse 7. And tangent is opposite over adjacent, 4.9 over 5. All right, now before we go any further with the next page of the notes, we're going to flip over and look at this page in a moment, but I want to show you a thing or two, and if you want to write this down on blank paper, you can. You don't have to. But these trig ratios, they actually work out as decimal values, and as I mentioned in class, your calculator is already programmed with every possible trig ratio for every possible angle measure. Okay, so if I were to work this out, okay, and I'm going to use a special right triangle as my example. I'm going to use a 30, 60, 90. Okay. I'm going to say that this is my 60-degree angle here. This short leg I'm going to call 3. Well, we know by our rules the hypotenuse would have to be a 6. Well, in this case, if I'm marking the 60-degree angle as my reference angle, the short leg is actually the adjacent leg, and the 6 is the hypotenuse. So I want to show you that if I were to do sine of this angle, but it's actually an angle measure, I'm actually going to write the 60, that would have to equal 3 over 6, because it's adjacent over hypotenuse. I'm sorry, not sine, cosine. Made a mistake. Let me fix that. Sorry, the cosine ratio is adjacent over hypotenuse from SOHCAHTOA. Okay? So the cosine of the 60 degrees has to be adjacent 3 over hypotenuse 6. Well, we can simplify that fraction real easily. That's just 1/2, right? Or 0.5. What I want to show you is I can actually plug that in my calculator and it will give me 0.5. So if I have my calculator, I'm going to find the cosine button on the calculator right there, and it opens up a parentheses for me. And I type in my 60-degree angle measure, and I hit enter. I get the 0.5. Now, if you're doing this on your calculator and you don't get that answer, there's a setting that is incorrect. Okay, I'll show you in class how to fix it because we're going to do some of these calculations together in class. But we're going to use the calculator for a lot of this to actually use some angle measures. Let's say I had some triangle like this, where this was, let's say, 53 degrees, and I wanted to know what that ratio was. Well, I don't have to know any information to find a ratio. The ratio of any triangle of this size, when this angle is 53 degrees, for, let's say, tangent, opposite over adjacent, I would just do tangent 53, and it gives me a ratio, okay? Now, that doesn't mean a whole lot to me, but I could use that in problem solving because the calculator has every possible ratio for every possible angle measure saved. So let's actually put this into practice and solve some problems. Okay, so in example 1, we are given this triangle where this angle is 42 degrees, this length is marked with an x, and this length is marked as 25. What they want you to do is use our trig ratios to set up a problem to find the value of x. So what we're going to do is we are going to set up our ratio, but first I want you to write your acronym at the top of your paper. So, on every problem, we're going to identify which part of that acronym we're using based on the relationship between the reference angle and the two given sides. So in this case, this is my reference angle. I always want you to mark it. Mark it up here, put an angle mark there, circle it. Whatever you want to do to mark that angle as your reference angle, that's fine, because that's going to determine whether this x is an opposite leg or an adjacent leg. I do know that it is a leg, and it is opposite that 42-degree angle, so I'm going to put an O there for opposite. This 25 is not a leg at all. It is, in fact, the hypotenuse. So I'm going to put an H there for hypotenuse. I'm only going to label those two sides. I don't need this adjacent leg. I'm not going to label it. This narrows my search down when I'm using opposite and hypotenuse. Really, I'm using the hypotenuse to find the opposite. That tells me I'm going to use the sine ratio. So I set up my sine ratio statement like this. Sine, and then instead of writing angle A or B or a symbol for the angle, I'm actually going to write the angle measure. Sine of 42 degrees is one value. It represents a number. That ratio is equal to this opposite leg x over the given hypotenuse, 25. Opposite over hypotenuse. Well, to solve this equation, we've got to get x by itself. That's what we're trying to do here. We want to get x all by itself in this equation. You can ignore what that number is over here for a second and just look. To cancel out divided by 25, what would you do? Well, you would multiply by 25. So I'm going to do that to both sides. I'm going to multiply by 25 on both sides. And I'm going to put that times 25 in front. Because what you're actually doing is 25 times the sine ratio for a 42-degree angle so that I get just what x is. And that part gets done in your calculator all at once. And again, I'll go over more of this with you in class. But in order to put that in the calculator, we're going to enter that into the calculator. 25 times sine of 42. So we hit our 25 times, type your sine button, and then enter 42. And you'll notice sine opened a parentheses for 42. I like to always close that. It won't make a difference on these problems, but it just is good habit to make sure you close whatever parentheses you opened. Hit enter, and it gives you an answer. That means, what this answer means is that the value of x here is about 16.7. And we're not told where to round to, so I'm going to let you round to the nearest tenth. We're going to call this 16.7 for x. Okay, so we're going to do another example or two, okay? We're going to do example 2. In this case, we have this angle measure marked of 75 degrees. Okay, that's my reference angle. So these two sides are related to that angle as either opposite, adjacent, or hypotenuse. That's going to tell me which ratio to use. So this length of 12 is across the triangle from the 75-degree angle. It is a leg because it is connected to the right angle. So this would be the opposite leg. So I put an O for opposite. This value of x that we're looking for is the other leg right next to the 75-degree angle, so it gets an A for adjacent. We're not using the hypotenuse. There's no variable there. There's no number there. So I'm not going to have you find that length right now. So I'm only using opposite and adjacent, which tells you the third part of our acronym SOHCAHTOA is the only one without an H. So that means I'm going to use my tangent ratio. I'm going to say the tangent ratio, and then right after it, I'm going to write 75. What that means is I would read that as the tangent of 75. Then I write equals. And then I fill in this opposite over adjacent fraction. Opposite is 12 over adjacent, x. Now, we haven't gone over how to solve equations like this where there's a variable in the bottom of a fraction. So I'm going to show you a little trick, and this will actually work for every kind of problem that we do in this lesson. We can treat this as a proportion. Remember, proportions are equal ratios or equal fractions, like A over B equals C over D. Well, this side is already a fraction. I have to turn this into a fraction. You might remember that to turn any whole number or any number into a fraction, simply put it over 1. That's a little unbalanced here, but you can tell this is tangent of 75 over 1 equals 12 over x. And to solve proportions, we cross multiply. Okay? So we're going to cross multiply here. When I multiplied by 25 on this side, I put the 25 in front. And so we're going to do the same thing. When I cross multiply this way, I'm going to put x in front of tangent of 75. That must equal the other cross product, 1 times 12. Well, that just stays 12. Now, we need to get x by itself. This is the part where you have to just rely on your algebra skills working on paper. I haven't gotten a calculator out yet. I'm just working with this on paper. To get x by itself, we want to get rid of the tangent of 75. But to do that, you have to divide. Remember, tangent of 75 is itself a number. We're not dividing by 75. We're dividing by the tangent ratio of 75 on both sides. So this is what I'm going to enter in my calculator. That's not your final answer. I don't want you to write it that way, but that's what we'll enter. Okay? And so I'll show you how to enter that. Okay, we're going to enter it very much like we just entered this other problem, but instead of multiplying, we're just going to divide. So we're going to start with the top number first, 12. Then we hit our division key, and then we can enter this exactly like it's written, tan 20, or 75. So we hit our tangent button here, right next to the cosine button, and then we hit 75, close your parentheses. Hit enter, and you get that the x value is approximately 3.2. And that is your overall answer. So here's what we're going to do. We are going to try and do some more of these in class. If you want to try these next two on your own, that would be a good idea, and we can check our answers when you get to class. Otherwise, we'll do more examples at that time.